Okay. So, buongiorno and welcome to today's physics colloquium. It is my great pleasure to introduce Professor Riccardo Sapienza from Imperial College of London. Riccardo did his PhD in physics from Lens Laboratory in Florence, and then he moved to different laboratories in dealing with photonics, mainly in Madrid, Paris, Barcelona, before becoming a lecturer at King's College in London. And then from King's College, he moved to Imperial College, where he is now professor of physics and deputy head of the department for research. But more important, Riccardo, in year 2000, graduated in physics in this room, because he's an alumnus of our university. And so I'm particularly happy because in spite of all the problems, with logistics problems with lectures and so on, yet our program in physics is still excellent because it can produce researchers as Riccardo. So I'm very proud of also this fact. So going back to close the personal note, so Riccardo is a worldwide expert in photonics, and he has a very extended experience in light control, in nanoscale architectures, complex lasers, and metamaterials. He is the director of the Center for Plasmonics and Metamaterials, and this year has been awarded a NERC Advanced Research Grant to explore programmable metamaterials. And these metamaterials is also the topic of today's colloquium. These metamaterials are fascinating new materials which have introduced a new paradigm in the control of light transport and light generation. And during this colloquium, he will also show a new experiment which extends the standard experiment we teach to our students of the interference, the Young's experiment of the interference of in real space of two light beams, and the extension in real time. So please, Riccardo.
Thank you very much. Thank you very much for the introduction. I tried to convince to give a talk in Italian, but it was not possible, so I do it in English. Yeah, last time I was here was many, many years ago at my graduation viva, the Laura at that time. So it feels really special to be on this side, and the room looks very different from this side than the other side. All right, so I will take you to a journey through metamaterials. I will show you first what are static metamaterials, which are still a development of the last 20 years. And then I'll try to bring you to temporal metamaterials, which is what really drives our research at the moment. And then the latest work, I will conclude with a spatio-temporal metamaterial, and how this becomes a motion, and all the things that we want to do in the future. So before I start, this is the team that is pushing the science. They are the one in the lab doing most of the experiment. And it's a very international team, and we have a very special collaboration across the UK, with Simon Horsley in Exeter and Imperial, but also across to New York with Andrea Lu and Emanuele Galiffi in Austin now. And they are mostly driving our theory support, because we are mostly experimentalists. OK. Let's start. So I think I cannot start an optics talk here in Padova without Galileo, of course, and the fact that the old optic, the traditional optics, is made of glass, as we know, and the way we control rays for centuries is by using the boundary between the glass and air. So we use the boundary conditions. You make a prism, and you get a certain property. You make a spherical object, you create a lens, and so forth. So this is all based on the ray picture of light. So if you think the light is a ray or picture, like in this photo, then you need a boundary to reflect light in the right way, create an image, and so forth. And what's very important of this picture is that when we have an interface between material, we can change the direction of the light. And the fact that we change the direction and not the frequency is because the frequency of the light is conserved, because this material is static in time. And so we have a translational invariance in time that gives us frequency conservation. So, and another way to look at this is to say that energy is conserved, because the system is translational invariance. So I can do an experiment in the future, I will have the same energy as now. Now, I say that, it's quite obvious, but later I will break this, so just to keep everybody on the same page. Then, of course, we know light is a wave, so we have a sinusoidal profile, and a wave has a certain property, can interfere, and also a wave has a certain size, which is the wavelength, which is the maximum between the distance between the maximum. So if you now take the wave picture of light, then you can design material that not only control the light through the boundaries, like we do with a piece of glass, but we can do it through the inside, the nanostructuring of the material. And this is an example, just a very random example of a material that you can make. And what's really important here is that the understanding that in a wave equation, the Helmholtz equation, the potential for the light, the effective potential, is mapped to the electric constant epsilon. Shows that if I design the electric constant in space, I can design the potential the light feels. And so I can, for example, create a certain potential so light can go in one direction, or I can create a focusing like a lens. So I can engineer any property I want through the potential of the light, which is the inside of the material. And this is the first concept. The second concept is also the concept of resonance. So we want to maximize the interaction. So we want this perforation, in this case, to be at the same scale as the wavelength of the light. And that will give us maximum effect. And again, this size of the order of hundreds of nanometers in the visible range. And the idea here is that we want to have a resonant interaction, a bit like a violin gives you a resonant interaction to a certain acoustic size. And if you change the size of the instrument, you have a resonant interaction to a different frequency. So once you combine resonances with nanostructuring, you can really maximize light matter interaction, achieve effects that are much beyond what you can do in natural material. You can slow down light, you can have light doing sharp bends, and many more. This is at the heart of all the science of metamaterial or static metamaterials. And I want to stress that a static metamaterial can control the direction of the light, as I said, because we are changing the special property of the material. And this was unlocked mostly by our ability to nanostructure material at this fine feature. And this is something that is done also here. So Professor Filippo Romanato here has a nanostructuring lab with electron beam lithography that can make this very fine, tiny structure. And this is what really enabled the first wave of metamaterials to be born. And what can we do with those materials? Well, we can make lenses, for example, that are super thin. So this is a lens made by nanostructuring these pillars in the right shape. And the lens itself is a few hundred nanometers in thickness. And yet it can focus the light as a macroscopic lens. And some of these lenses will be in a mobile phone. Samsung bought one of the first patents, for example. So this is something that is coming to reality. But you can do much more than just focusing. Of course, if I choose the right phase delay, phase structure, I focus the light. But if I do something more complex, I can create a material that converts light into a much more complex light beam, not just a spot. So this is, for example, depicted in this picture. I can create colors without having any pigment, because I can have material that reflects a certain color and not another color. So this is an example that we made for a science exhibition. So we had a little flower nanostructure. And this can be applied to any material, regardless of the pigment. So for example, this was done on chocolate. And you can have a colorful chocolate without pigment. This is just nanostructured chocolate. Of course, this was done in ETH in Switzerland. Of course, that's for the chocolate. And you can do much more. You can control any light process. So you can control absorption and emission of light. So for example, you can create a nanostructure that can boost the light emitted by a molecule that is in this material. And this is, for example, done for erbium in silicon. And this is a work done by Boris and Giovanni here, and Tiziana. And where we have seen that this can really give you 100-fold enhancement of the emission of light. You can also go to material to responses that are not so clear, so obvious in nature. For example, one can create refractive indexes that are negative by nanostructuring and combining metal and dielectrics. And so you can have material where the energy flows in one direction, but the phase goes in the opposite direction. That you can describe with a negative refraction, and then it give you this kind of, if you were able to do it on the macroscopic scale, you will see something like this. And then if you design even further, you make a more complex device, you can really shape how light waves propagate. So you can make a cloaking. This was something that hit the news very much 10 years ago or so. So you can have the green is the metamaterial around this object that is designed to shape, to let the wave go around the object and reform a front on the other side, which is exactly the same as the one you would have if you had no particle at all. So this object then becomes invisible. Whereas if you didn't have the metamaterial, this object would scatter light, and you see here the wavefront is very different, so you can detect it. Now, this has triggered a lot of curiosity, of course, and in principle, one can create any shape. The limit is really how well we can fabricate this structure. Can we really make something that is so precise and works at all frequencies? And there's many more. Now, the last example I want to show you is from our recent work, where we have created metamaterial that can emit laser lights in the shape of we call it a network. And the light is trapped in this material because of multiple interference and scattering. And this is a very strange laser that we can use for computation. So when we illuminate a laser with a certain digit, in this case it's number 4, we have a certain response of the material that is very easy to categorize. So we can perform the same calculation you would do on a neural network in your silicon chip. We can offload it to the physics, and this becomes much more efficient in terms of energy and much more efficient in terms of what you can extract, how much information you can get. And again, we made a spin-off now on this area, and if you're interested, just look at the link. So metamaterials are already there, are about to be everywhere. I would say anywhere we have a photonic interaction, there will be a metamaterial. It will be on windows, it will be on glasses, it will be on computers. It's already on solar cells to boost the trapping of the light, for illumination, light guiding, laser, and I would say many, many more. So if metamaterials are so well engineered, so why am I here talking to you? There is a bit more. And what's more is that so far we have exploited the spatial degrees of freedom. We have designed material that varies in space. But what if we were able to design a materials that instead is nanostructure in time, which has features that varies in time, so that we can design a potential for light in the temporal degrees of freedom. And this is really the question that we have been trying to answer. There's been 30 years probably of theoretical work that imagine what if I can do this. And only very recently, in the last 5 to 10 years, we have experimental evidence. And I think this is becoming really an exciting topic. So let me now slow down and try to understand what is a temporal metamaterial. So first, I like to take a symmetry point of view. So as I said, if the time is invariant, then we have a conservation of energy, which means that the frequency is not changed. So a spatial metamaterial can only change the direction of the light. If instead I have space to be invariant and not time, then I will have the direction is conserved. So the momentum of the light is conserved. And instead, a temporal potential would change the frequency of the light. So we can intuitively get this from purely a symmetry point of view. So a temporal potential will change the frequency of the light. That's, of course, not only that. And let's see more. So if I have an interface in time, and now I'm imagining no space at all, just to simplify. So let's imagine that this entire room changes optical property at time 0, homogeneously in space. So there's no special component. So a wave is propagating at time 0. The room changes optical response. So what will happen to this wave that propagates? So the first thing that can happen is that the wave keeps on propagating, but now in the new medium, after time t0, we'll have a different frequency. And this can be described by the Snell's law, the same law that we use for ray optics to discuss direction of light from a piece of glass. But now the Snell's law tells you that the product of the frequency and the refractive index in one side has to be equal to the product of refractive index and frequency on the other side of the discontinuity. And this has been measured. This is the first paper in the group of Boyd. You see here, this is the frequency measure of a light beam. And on the vertical axis is time. At time 0 here, the modulation occurs. And you see that there is a jump in the frequency that then recovers at later times. So we can change the frequency of the light, and this is what we call a temporal refraction. So light goes through the discontinuity and change frequency. But we can also get temporal reflection. So in a spatial reflection from a piece of glass, we send a light beam, there's a window here, light comes back. So we flip the sign of the direction of the light. And we call it the momentum of the light, so we flip k to minus k, the direction of momentum flips. Now, what if we had a temporal interface here? So if you have a temporal interface, what you flip the sign is a sign of the frequency. So we start with omega, and at the time 0, we generate negative omega. And then what does it mean? So what it means is that we don't change the k, so k stays in the same direction. But if omega is flipped, you see here in the simple plane wave, if omega is flipped, as time progresses, the phase, instead of progressing, reverse. So this wave behaves as if it was traveling backwards in time. And this is the moment where nobody believes me anymore. And so because of that, I show you an experiment to prove that this is not completely crazy. Now, the experiment that I show you is done in water wave in a group of manual fort. And a water wave is a lot easier to visualize. So bear with me. I will go back to optics in one slide. So this is a smiley face that is imprinted on the water surface. And then there will be a wave that it will be emitted from this smiley face. And then at time t0, the researcher kicked the bath, which is equivalent to create a temporal discontinuity. Now, it's changing the impedance for the wave. And so you can imagine that I'm changing the refractive index of the system. And then you will see that at time 0, there is a wave that propagates backwards as if it was propagating backwards in time. So this is the wave is launched. And then at time 0, they kick the bath, and you see there is a secondary wave that is reflected that reform the smiley face in the middle. Do you see that? So this is a wave that propagates as if it was going backwards in time, because this phase is now going backwards. OK, so this is what happens when I have one temporal reflection. I can put many together. And if I put many temporal reflections, imagine I have many temporal discontinuity, I can do it in a periodic fashion. And if I do that, I can create what we call a time crystal. And I have to be precise, this is what we call a photonic time crystal, because there is another family of time crystals which are different. But it's just a detail. So in a normal spatial crystal, which is a series of different material, different epsilon, different refractive indices in time, I can create band gaps similar to the one for the electronic system. These are energy band gaps. So there are energy range for which no states exist for all direction of the wave. When I have a time crystal instead, I'm flipping space and time. So now I have a modulation that is homogeneous in space but varies in time. And if I do that, I can create a gap, but this time the gap is also flipped. So it's in a momentum space. So there's a range of frequency of momenta for which I cannot propagate in the system. But in the frequency range, I don't have any band gap. So again, we are changing. There are a few other interesting things about time crystal. For example, the fact that there are two solutions in this gap, one that is attenuated exponentially, which is what we expect. But there's also another one that is exponentially growing. And again, I don't want to enter the detail, but there's a lot more there. And also, we don't know how to make them yet. So anyhow, let's keep on going. What I show you is that when I have a temporal modulation, I can control the frequency degrees of freedom of my wave. But I can do more than that. I can break fundamental symmetries. I can break energy conservation, of course, because I change the frequency. But I can also break reciprocity. So for example, reciprocity can be said colloquially in if I see you, you see me. The fact that the amplitude of going from A to B equal to B to A. In this case, reciprocity can be broken, which means that I can have wave that propagate in one direction, but never come back with the same probability. And I will show you that there are more things. So this is really interesting. And let me show you now how we do that in the experiments. So how do we create a temporal interface? And what I didn't tell you is that to create a very good temporal interface, I need to be able to modulate the material on time scales comparable to the wavelength, to the period of the oscillation of the light. Similarly to the spatial case, where I need to have an interface that is faster than a wavelength of the light. So making a shape which has a micron in size is not that hard. I don't want to say it's easy, but we can make a Windows, and it's actually sub-micrometer flat. But to make something that changes in time on a few femtosecond time scales, that's really hard. So that's one of the reasons why the experiment took so long to do. So how do we do that? To do that, we're using a very ordinary material, which is indium tin oxide. So this is a material that covers your mobile phone. It's a conductive transparent oxide. So it does not absorb light, and at the same time, it has a very low conductivity. So it's one of these right balances between properties. And this is a material that has been engineered for computers, mobile phone. It's on every screen almost. But at the same time, it's a material that has a very peculiar response to optical excitation. So when we send a very strong laser beam, which I picture here, into the material responds by changing its refractive index. And this is the typical picture that we have in mind. The refractive index is the refractive index without any excitation, plus a term that depends on the intensity of the light that drives the material. Now, this is the work of Stefano and Romain that started this in our group. And this is, for those who know, is called Kerr effect in nonlinear optics. But this picture in reality is not completely correct because we are not in the perturbative limit. We have huge changes of n. But this picture already shows you that if I have a material where NL, so this refractive index without excitation, to be really small, then these terms N2, which is the one in front of I0, becomes very big. So ITO has one property that has a point which we call the epsilon near 0 point. So its refractive index goes close to 0 in a certain frequency range in the near infrared, around 1.3 micron. And we can exploit that to boost this optical modulation effect. A more condensed matter picture is that we have a material that when we excite it very strongly, the electron go to higher excited state, and they probe a band with a different curvature, I up, because of the property of the band structure. And so they will realize a material with different optical response. I have to say that there is still a lot of debate of what's really happening in ITO. Why do we have a big switch? There are models now put forward with also Auger component and other details that maybe I shouldn't be talking now, but what we know is that this material works. It has two real properties for us. One is that it switches very much, but the other one that it resists very, very intense laser pulses. So we can put really high intensity here without melting the material. Now, if it was a month ago, I would say this is the only material that works. But I think we have now experiment done in the group of Giovanni here that shows that maybe there are other materials that can do this as well. So, and I think there should not be only one material that can do that. But I won't talk about it. So how do we do it in the lab? We have a femtosecond setup. We have a very short laser pulses that we are sending to the material. Those laser pulses will trigger the response of the material. Now, in a simple picture, we excite the material, the refractive index jumps. And this jump is of the order of unity, which is really large, in times of the order of sub 10 femtoseconds, which are close to the oscillation of the light. And then we send a second beam, which is our probe beam, that will is the beam that will feel this modulation of the response, that will feel this temporal potential that we are designing. And I show you the result of the experiments. So this is a measurement of the reflectivity of this layer that changes when we excite the layer. And you see here that the reflectivity starts very, very low. We are of the order of 7%. And then when we increase our pump beam, the reflectivity goes up, approaching 80%. Now, I want to remark that these numbers are really high. We are talking about hundreds of gigawatts per centimeter square. And we are actually now also extending to terawatt per centimeter square. So these are clearly numbers that require a femtosecond laser. But on the other hand, this is a pure physics study. So I don't mind too much that this is a bit high, as long as the material doesn't melt. But for application, of course, one has to think twice. Again, a little parenthesis that everything I'm telling you today is about light, but can be easily applied to any other wave. So if you're able to modulate an elastic wave, you will achieve a time-varying metamaterial. And there are many experiments in other waves as well. And for those waves, it's a little easier to modulate. So it's not just this case. OK, so what happens if I then send my probe on this modulating material? So in the temporal domain, I will see a probe that now is, for example, the blue light is my probe, and this is as a function of time, my pulse, and the vertical is intensity that I measure. And then when I switch on my modulation, you see at time 0, you see that there is I create a huge cut indent in my probe. That's because the reflectivity is going from almost 0 to very high, to almost 100%. And so the light is not going through the material anymore. And the higher I pump, the deeper this goes. Yeah, I won't tell you how we measure this, but this is a technique called frog for the specialist. Now, the temporal picture doesn't really tell you everything. It's a lot easier to work in the spectral domain. So we can look at the frequency of the light that we are sending in, and which is what I plot here. So you see we have a beam that is centered around 232 terahertz, which is 1.3 micron in the infrared. And the vertical axis here is going to be delay. So at this point, we are very far away from the interaction. So it's a pure beam that we send in. And then at time 0 here, it's the time where the wave is interacting with the modulation. Is the 0 of this interaction. So if I look what happened in that regime, then you see that I have a new frequency that are generated, like the spreading over, in a also not very simple to understand way. And this new frequency come exactly at the modulation. Now, if you are in photonics, you know what a Mie scattering is. This is the temporal analogous of a Mie scattering, but this is a temporal Mie scattering. So there are a lot of interference fringes here that come about. But another way to look at this is to think that this is a time slit. So we have changed the reflectivity of the material very quickly at a given time. So you can think that we have created a slit in time, which is similar to what you do in space when you make a hole in a screen. That's a slit in space. Now, this is a slit in time because we open it for a little time. Now, this is a bit asymmetric. It's not exactly square because the material response is a bit longer on the other side, but these are details. OK, so I have a time slit. I send a wave at a specific frequency, and what I get out as in reflection is many new frequencies generated, which is the diffraction from a time slit. Now, if I can make a time slit, of course, I could also make a double time slit. It was a very clear step for us. We actually, in reality, we were really troubled by how to explain this. All these interferences are very hard to catch by theory. But then when you move to double slit, it's a lot simpler to understand the theory. So, OK, what is a double time slit? I shouldn't say anything like that. I explain it to a physicist cohort. But this is an experiment that we did in the lab. I did it for my undergraduate student, actually, during a lecture. So we took an attenuated laser beam. We send it to 2 holes in a screen. And then on the right here, we have a single photon camera that can detect single photon. And you see that the photons arrive individually, but they form an interference pattern, of course. We all know that. This is fairly old. So this is the spatial version of the problem. So again, just in this picture, just to make it simpler, from each hole, I will have a spherical wave and interference in the far field. And I usually will illuminate the screen with a beam that is larger than the separation between the holes. Otherwise, this doesn't work. So what is the temporal version? We have now 2 times modulation in the material at different times. So each time we change the reflectivity to high and then low, and then high and low again. And we send a wave into this material. And then if you think, so each of these photons that we send can either be reflected by the first interface or be reflected by the second interface. But in reality, they will do both. And each time they will generate new frequency, and then we'll have interference of the light that is interacting with the material. And now, of course, we do expect interference, but in which domain? So let me show you first how we do the experiment. But we have a double pump that goes into our material. So this is the shape of our double pump. And we change the reflectivity twice. And then we send a probe beam that is longer in time than this double modulation. So then we can collect a full interference. So yes, we expect interference. And the interference that we observe is in the frequency domain. So we have a new frequency generated away from the central one, which is outside of this plot. And you see there is a pattern here that is very clearly interference pattern. And below is what we expect from the theory. So this works. And then if we have a 800 femtosecond separation between the time slit, if we change it, as expected, if we make it shorter, we'll have larger fringes in the Fourier domain. And you see here that we have less oscillation or wider, a longer period in the frequency domain. So this works. We have an interference as expected. But what's really surprising for us was that the decay of this oscillation, so they go down to 0, this has a shape which is related to the sharpness of a single interface. So if you have a perfect vertical interface, like in a special case, this will go down as 1 over f squared. And if you have a very blurred interface, this may even not go down at all. So it would be very different. If you have a very blurry interface, this should be very, very, very sharp, and you will not have any interference. So by fitting this oscillation pattern, we can estimate the response of ITO, how fast we switch in the material. And here we got the surprise that we are below 10 femtoseconds. So the material responds really, really much faster than thought, which is the reason why we can do all these experiments and these potentials. OK, so I show you how we can design modulation first in space alone, then in time alone, and then, of course, now it's time to put them together and do spatio-temporal modulations. So when I combine them together, I'm thinking about combining very fine modulation in space, of the order of 100 of nanometers, and at the same time, very fine modulation in time of the order of femtoseconds. Now, this is the ideal case. Then, of course, we can afford to be a bit longer in both of the domain, and we'll have a smaller magnitude of the interaction. Now, I really want to stress that there is a huge body of activity in this area. And here I just put a few articles of multiple groups that are working in this. And this is becoming really interesting. And there's a lot of work in combining space and time and spatio-temporal interaction. Now, my take is to look at combinations that are non-separable, which I mean I don't want to study first a spatial modulation followed by a temporal modulation, which is separable in 2 steps. I really like to have them happening at the same time. So if you have, at the same time, a modulation in time and space, now this is a bit difficult to picture, so I try with this plot. So I want a refractive index that varies both in the space domain and in temporal domain, but not separately. So if I do at the same time, what I'm thinking is something like a refractive index that moves at different positions at different times. So what you really see that by combining space and time, I can access motion. And this is really unique of these space-time metamaterials. And if I have motion, of course, I will have a velocity. I can have an acceleration, and so on. So how do we do that? So in the experiment, let's imagine that we have 3 laser beams that we can independently control with 3 laser pulses that are very short, which are my red picture here. So if I send them on the material at different time and different position, like I do here, then I will have 3 modulations that will appear on the material at different time and different position, of course. But if I make this as a sequence like I've done here, then imagine that you have a wave that propagates on this surface. Now, this wave will feel a refractive index that travels on the surface. And I can design this velocity by purely designing when this modulation occurs. And what's really interesting for me is that I can design this free from any relativity limits. So I can have a superluminal modulation very easily. I mean, if I have these 3 appearing exactly at the same time, I will have an infinite velocity, because the refractive index will appear instantaneously everywhere. And if I slow them down, I will have a smaller velocity. So this is a playground for motion, for experiment where we interact matter that moves with light. And the other very important thing is that from the point of view of the wave interacting, this motion that we call synthetic motion, because no matter is moving in any way, so each of these electrons in this area are not traveling, they're just being excited or not. So it's synthetic motion. But from the point of view of this wave, this synthetic motion is exactly the same as a real motion. So the wave will see a reflectivity that varies in space and time. So this wave will not know that we are pretending to move. And the experiment that we can do are the same as if we had a superluminal interaction. And let me show you how we do it. So in experiment, we actually, at the moment, don't use multiple laser beam. We use a single laser beam, but we send it with an angle to the surface. And so when we send the laser beam to this angle, again, this is our ITO. When the laser goes on the surface, interact with the surface at different position at different time. And exactly this angle will define a velocity, because all the points will depend on the angle of the incidence of this beam. So by changing the angle of the beam, I can change the velocity. If I was to enter normal incidence, I will have infinite velocity. And if I enter in this direction, I will have a velocity equal to the velocity of the wave. And in between, I can play. And this is what you expect. So it will have a velocity that will diverge if my angle is 0, and go down to C when I am far away. So we are doing experiment in this range. We are around 60 degrees. And so we have now 3 velocities. And at the same time, we are sending a probe beam in the same way. So the probe beam will have velocity also that depends on the angle of incidence. And I will show you that the probe is going to be in the middle here. And I have 2 modulations, one slower and one faster than the probe beam. So one subluminal and one superluminal. Now, another way to look at this is to think about a Mexican wave. This is an animation that Anthony did, one of our PhD students. I really recommend you see. This is incredible what he managed to do. So if you have a Mexican wave, you start from this side, and it travels around. Then you see people go up, and the velocity of this wave has nothing to do with the velocity of the people. Because you can be very slow, but if you decide to synchronize, you can move very quickly. This is the same concept. Another example is the laser pointer on the moon. I don't know if you have heard of that. So if you have a laser pointer on the moon and move it, this moves faster than the speed of light. But actually, light travels in this direction, not in this direction. It's only the position of the beam that travels, not the light. So it's the same idea. So it's all synthetic motion. It's the fact that we are engineering a motion without anything moving faster than the speed of light. OK, sorry. Now, what can we probe? So we want to send a probe and interact with this material. So you are very familiar with Doppler shift. So if we send if you have an object traveling at a certain velocity, you will, and emitting light, you will have the light wave being compressed on one side and not the other side. So we have a change of pitch, red shift and blue shift. That's the same as an ambulance coming towards you. You hear a pitch that changes when they cross you. OK, this is all clear when you are subluminal. If we go superluminal, we can do the same picture. Now, superluminal, everything flips. This is what people call the inverted Doppler shift. So now the red shift is on the front and not on the back, and blue shift goes to the other side. And that's because now the velocity, so the object is traveling faster than the wave they are generating. So I want to show you this, and this is the guide of our experiment. And I discovered there are a lot of experiments in inverse Doppler shift, so I put the one reference here. Right, so this is the experiment that Stefano, Anthony, and Rasman did. We have a probe beam that is the green one, and the red beam that is our pump beam, the modulated material. They come with an angle, so this generated traveling modulation. And then we detect the light that comes out. And it's very important that we detect both in frequency and in momentum now, because we are looking at spatio-temporal interactions. So we are looking at, I show you plots like this, where on the vertical axis is frequency that we detect, and on the horizontal axis is angle, which is a measure of the direction of the light coming out. And so we basically look at the light that comes out, and for each angle, we measure the spectrum of the light that comes through. And so first we do the experiment for subluminal interaction. The red box is the light beam that we send in the probe. So this is what's already in the beam. And then you see that we have a tail that comes out. So this is the result of the diffraction effect, or this is the Doppler shift, if you like. You see that there is a new frequency generated, but also they go in a certain angle. So there are also new angles generated. And there is a correlation between this angle and the direction. Now, the white dotted line is the analytical theory from the Doppler shift that Rasman calculated. So you see that this is what drives our diffraction. And if you compare with the simulation, this was done by Simon Horsley and Calvin Hopper in Exeter. You see that the simulations are fairly similar, and also they follow this analytical theory as expected. Now we can change the angle of the pump and go superluminal. And when we go superluminal, we have a flip of the sign. It's a signature of the inverted Doppler shift. So now the frequencies generated are generated in the opposite direction. So the light that comes out, now it comes in the opposite direction than before. And again, we can capture this with our model. So we can do this interaction which I call diffraction, or you can call it Doppler shift. And this is done for a single velocity. Then, of course, we can do much more than that. We can go acceleration and so on. But before I show you that, if I have still 5 minutes, I will want to show you what we can do with spatio-temporal modulation in general, to trigger also application and technology. So what can we do? First, I told you we don't conserve energy. So yes, we change frequency, but there's more than that. We can also amplify and absorb light from the interaction. And this is an experiment where we have a big pump. The pump a system where an oscilla and a signal. Now, I don't have the time to go into the detail of this experiment, but this is equivalent to the temporal coherent absorption that some of you know in the spatial domain. But what we see is that by playing with the modulation and the phase of the modulation with respect to the signal, we can absorb almost completely the light beam that interacts with the material, or we can decide instead to change the phase and amplify it by a factor of 4. So there is an exchange of energy between the modulation and the light beam. So we don't conserve energy, of course, but we can play with that, either to absorb or to amplify. And this has been done also in other domain. So this is in the microwaves. And in this case, you can even engineer the phase of the modulation much more precisely because everything is slower. And this is an experiment that shows similar results. And then in theory, and this is a theoretical work, you can even achieve lasing without any gain. So you can amplify so much the light that you have light that comes out from the interaction that look like a new laser light. So you can really achieve amplification like in laser by using the modulation. Also, we can break time reversal symmetry. So again, these are experiments done on a meta surface where by modulation you can have a beam that interact with a meta surface and goes in one direction. But if I send the same direction back, it does not go towards the blue, it goes towards the red. So we have broken the time reversal symmetry. And this is very important to create circuitry where light flows in one direction but not backwards, which is very difficult to do. This is done in acoustics. This is a circulator. And you see a circulator where light circulates in one direction but not in the opposite direction. So you can, again, engineer all this by basically splitting the interaction due to the modulation. Even more, every time we have a temporal modulation, like in this picture, so at time 0, there's a sharp change of the response. Theory says that we generate photon pairs. And those photon pairs are entangled photon pairs. Now, this is theory only, so I will tell you if this is possible in a while. And it could be that these pairs are very weak. I mean, the brightness is what makes them useful for quantum technology. But this is something that has been predicted in multiple ways, especially related to motion. So every time we go superluminal, every time there is a superluminal interaction, there is a photon pair generation from the system. We can control the momentum frequency of the light, so we can generate, as I showed you, diffraction, but we can also take a beam and split it in two components, the blue going left, the red going right, as in this picture. And very recently, this has been also done electrically for light waves. And this experiment is really interesting. Of course, the modulation is very, very tiny when you do electrically, so it's not as large as the one I discussed here. But it's very useful if you have a very narrow band laser. So a very narrow band laser can then be switched from left to right by changing, applying a bias to the material. And then, of course, the electrical modulation really opens to application much more than our femtosecond laser. Even further, so if I push the analogy, I said that when we design a material in space and time, we are designing a potential for light in space and time. And if you're able to do it in a programmable way by illuminating in a special way the material, we can program a simulation of an Hamiltonian, for example, or any equation on the material. Now, I'm not saying this is tomorrow, this is the future, but I think we could do that so we can have then an input beam, which is an input state that we make interact with the material, and looking at what comes out, we'll have the full solution to the problem, either in terms of analog computation or simulation of another physical principle. So this is very interesting because for the first time we have a knob that we can play to control spatio-temporal potentials. And then if we really move even more to the future, and bear with me with that, if we are able to control space and time fully, it means that if I will have an input beam, I can convert into any beam I want with any spatial component, any frequency component, which means that I can create the ultimate hologram, which has any shape and frequency that I want. Now, we are really, really, really far from this. So this is probably impossible to achieve. This requires high efficiency, very high dimensional control, all things that we don't have. And so do not believe me on this. But what you should take here is that if we control a material in space and time, we can engineer any interaction that we like. And so this is the ultimate control of a light beam. And therefore, I think this will serve a lot of surprises, much more of what I just talked you about. And so with that, I'd like to conclude. I show you that we can control frequency, momentum, amplitude of the light by designing a suitable modulation. And I think the future is in the combination of space and time. And with that, I really hope that you enjoyed it, and I thank you for your attention.
Riccardo, for this beautiful talk. So I guess there are questions. Questions? No. Yeah.
Thank you. Yeah, so thank you for your talk. It was really interesting. I think I just missed maybe the most important link, namely in slide 44, how do we really get from this, like from these slits in temporal space or in time to actual like this wave effect of superluminal motion? And then also like why is it that, because like the maximum wave exists already, so like why does this time slit actually induce this superluminal effect? Yeah, I mean, is the important link what I think.
Yeah. So the way we design this is by having a material that changes a different position at different time. So really, you can imagine the way I show it here, that you have a 3 laser beam with 3 very short laser pulses, and we can control the delay in which they arrive. So we can fairly easily have a laser pulse arriving at time 0, another one arriving 100 femtosecond before, and then another one 200 femtosecond before. So I can have these 3 positions excited at 3 different times. And then, so if I am a wave traveling on this surface, I will see at time 0, I will see the modulation at my position, and at a later time, I will see this reflectivity change to be in front of me. It's a bit like in a Maxim wave if you were walking around the stadium. So you will have a modulation that travels next to you, slower or faster than you when you travel around. I think that's the way we do it.
Let's say this material has different spatial refractive indices, and then you let it go through this material, which has a different, let's say, in one direction, a different refractive index. Then you also have this net slowing down of a light beam through if it goes through a material, and then at the outer end, it might also produce such an effect, right? Like if you
the wave velocity depends on the refractive index, but that's a constant background. So that would be this wiggle will travel at the velocity that depends on the effective refractive index that it feels. But then when you see these bumps, these are an additional modulation on top of that. So if you want to have a background, and then on top of that, you have a change of refractive index that travels.
Okay, thank you.
There is a background, of course.
Questions? Yeah. Rico? I go. Bye.
Yeah, thank you, Riccardo, for this very inspiring talk. I continue with exactly this example. When you have a clearly explained with 3 times pulses, but what is the effect of space dependence? I mean, you have metamaterials there. A metamaterial can have any spatial modulation. So it's not clear to me in this case what is the relationship between x and t. So which is the effect of space when you have 3 pulses with different space modulation that you just described?
No, I think you are going too far into this slide, because in this slide there is no spatial structure. So I understand your question. So you're saying, what if we have also a static spatial structure on the material? Then I will have a much more complex interaction. Yes, this is an. So in this experiment, this is a very flat ITO surface. No, it's not a structural metamaterial. It's not a spatial metamaterial. Yes, and this is what, for example, the paper that I, too much, come on. In this paper, for example, they use a real spatial metamaterial, and then it's modulated, but modulated uniformly, so there's no motion. So what you're suggesting is still a big step in the future. So being able to have a material that has some shape that interact in the right way with a traveling modulation. And nobody have ever done that. So that's really interesting, but I don't know the answer.
Thank you very much, Riccardo. One question about the probably the most intriguing part is the non-conservation of energy. And you mentioned that you can exploit for amplifying emission lasing. Which are, can you elaborate more on that? That is, which are the challenges from a technological point of view to reach lasing maybe out of these materials in the visible range, something like this?
So I think lasing, we are very far. So this is our experiment where we are looking at this energy exchange. So the heart of this is that my beam that I send, my signal beam, can interact with the modulation coherently, so it can exchange energy with the modulation. And this is driven by the phase of the material, in this case, in this specific geometry, the phase between the wave, the signal, and the pump. And so what one can do is really, and this is very similar to a parametric amplifier. It's working the same principle. Now, if you are able to go above a certain threshold where the interaction is cumulatively exponentially growing, then you can reach a level where you go above a threshold and it lays. Now, in this experiment, we don't do it very well because the interaction length of our light in the material is very short. And this is the problem with the ITO that has absorption. So you can't really go deep into you cannot do a millimeter waveguide in ITO or anything like that. So if you were able to have a long interaction length, which means a modulation that travels with the wave for a long time, then you can really amplify more and more and potentially go above threshold. I think what we need is a material that can modulate very much without absorption, which is the challenge, has always been the challenge of metamaterials. And I don't think we have it. So the ITO works well, but it absorbs a lot. That's the reality. There is a question.
So, I just want to ask, when we speak of superluminal motion, do you intend to say that it is possible to send information faster than light?
No.
Okay.
No, that's exactly what I don't say. No, of course we can't. We can't break relativity. I have no intention. What I mean is that from the point of view of the light wave traveling, there is a particle coming against the wave that is traveling faster than the speed of light. But there's no point, any signal that travels faster than the speed of light, because there's no actual matter that travels, or light that travels faster than the speed of light. It's the same way as the Mexican wave again. So you can look like you are transferring some information to the other side, but that's because you have pre-synchronized the wave. So the reality is that every person moves only half a meter in, in 10 seconds. So it doesn't move faster than the speed of light. So no, the answer is no.
Thank you.
No problem.
So thank you for your fascinating talk. I have a couple of questions in one. In general, what is the role of noise and defects? I mean, in static metamaterials, you mentioned you have a modulation of the, okay. So do you have any evidence of the role of the defects or even quasi-crystals, if possible? And in the dynamic metamaterials, what is the role of the noise? Because you mentioned that you need fast modulation of the order of optical cycles, okay, but of the order of unity. So what is the uncertainty? It is always small or not? Thank you.
So this is a very interesting question. I think I have a lazy answer, and then maybe I'll try a better one. But the lazy answer is that we don't worry too much about that because we are at a very early stage. So if I was able to create a time crystal, then I could ask myself what's the role of defects, but we are very far from making one. So we have a single interface, or double. So we are happy with noisy results because this is a very early stage. That's a lazy answer. On the other hand, I think defects are very important, and interference has the same role. So if I had a perturbation in my series of modulation, I will have the same problem in interference. And so I will end up with a washout interference if the noise is too large. So if you extrapolate to when we are able to do quasi-crystal, we will have the similar physics as you can do in a time crystal, in a spatial crystal, from the point of view of the noise. Then there are other effects because these systems are very nonlinear. And so there is amplification and so on, which is nonlinear, which means they will depend differently to defects, because a static crystal is linear. So I think it will be different, but we are 10 years ahead to be able to answer this question, at least.
I've been intrigued by the spatio-temporal modulations, so I have maybe a naive or possibly ill-posed questions about this. Is it possible to conceive of light detectors which are very fast and work at very low light levels, very dim light?
I have to say I have never thought about that in this contest. You mean from the spatio-temporal modulation?
Well, if you think so, but
in principle,
in general.
In principle, yes, in the sense that this is a way to streak the light out. So you will end up with light at different frequency, different direction. So you can use it then to be able to map what light was inducing the modulation. So in some way, reverse engineer and get a temporal response. The efficiency are very low. So I don't think this is really very useful for detection. So there's been an attempt to create a streak camera out of the modulation. This is in a group of Shalev in Purdue, where they use this kind of spatial-temporal modulation to create a streak, like in a streak camera, with the idea of making a detector. But I think we are, I would say in optics, maybe not now. In other wave domain, I think it's very different. That's maybe possible. I don't know, I don't have a good answer for that.
No, I was thinking of very fast light detectors for astrophysics, for instance.
No, I don't know.
Large and fast, extremely fast.
And efficient.
Other requests? So like, okay, let me go.
Thank you for the talk. I just wanted to ask if there is any particular property of the ITO to be used at material for temporal modulation. I can imagine that maybe it's for the dispersion properties of the electric function, but I don't know if you can point a particular one.
Well, there are two properties that are really crucial. So one is the non-parabolic bands, which we need to be able, when you excite, to have a different response. The other one is a very, very high heat capacity of the electrons. So that the material is able to absorb a lot of energy without melting the lattice. And so this enables us to have this huge excitation. The electron temperature goes to 10,000 degrees or more, but the material doesn't melt. So I think it's a lucky combination of those two. I have to say, because we don't understand fully ITO yet, maybe there's something else. But thank you.
More questions? So if not, let's thank again Riccardo for this beautiful talk.